Hello, we're doing section 9, acid anhydrides. Now, the way to prepare acid anhydrides are twofold. The first way is that you can take a carboxylic acid, okay, and two of these basically can come together. So you use two equivalents, for example, and you heat this up to very high temperature. Okay. Now, the boiling point of acetic acid is 130, if I remember correctly, something around there. So 800 degrees Celsius is a very high temperature, and this would have to be done in a pressurized vessel to contain all of those superheated liquid. And this forms acetic anhydride, and this is how it can be done industrially. And that releases water. Okay, so there's, of course, an equilibrium. So it's going to be influenced by temperature and pressure and things like that. Now, that's not very practical, but I do want to mention that you can very easily do this with something like this. This is phthalic acid. Okay. And if you heat this up, you know, of course, we're using two equivalents. I'm not balancing this chemical equation. I'm sorry, here we use one equivalent because you have two carboxylic acids. And from this chemical reaction, you form one equivalent of something called phthalic anhydride and water. So you know by entropy, if you increase the temperature, you're going to drive this reaction to the right. And this product here can be sublimed and collected quite readily, and that might only occur at around 150, 180 degrees Celsius, pretty normal room temperature reactions. The starting material and the product are both solid, so that's an easy reaction to carry out. Okay, I just wanted to mention that. Now, we don't normally do this in synthesis. Okay, we're not going to take a carboxylic acid and heat it to ultra-high temperatures because some of the sensitive functional groups can cause decomposition in the organic molecule. The best way to make an acid anhydride is to start from an acid chloride and then react that with a suitable nucleophile, like a carboxylate. Okay, and that will make the anhydride, and of course, you'll lose sodium chloride from that. Okay, so recall again that if you take a carboxylic acid, okay, and you treat this with sodium hydroxide, for example, you can make the sodium salt of that, all right? The reaction mechanism involves nucleophilic attack, okay, of the carboxylate onto the acid chloride. So remember, again, you want to go through that tetrahedral intermediate. You want to push the electrons up to the oxygen. So that's the attack step. And you get the tetrahedral intermediate. And we'll draw this all out here. And this can collapse by expulsion of chloride, which is a good leaving group in this case. So the mechanism is AE, attack and then eliminate. All right, and you can do that for any kind of carboxylic acid you want to do. Okay. In the textbook, they give you all of these reactions. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different reactions they show there. They don't show the mechanism for any of those. They say, okay, these are 11 new reactions, just learn them all, and they work exactly like acid chlorides. If I was teaching face-to-face with my class, I would say exactly the same thing. Review acid chlorides, just replace the chloride with acetate and go on from there. Now, since I'm teaching, so if you understand acid chlorides well, you can just learn those reactions, add those to your flashcards, and stop the video now. But since I'm teaching online and I have the opportunity to make a video for people who might be struggling, I'm just going to go ahead and write down every single reaction and then work through the mechanism, which is not shown in the Klein's textbook, okay? But the mechanism is exactly like chloride, okay? So first things first. We've already talked about this reaction here. Okay. This is how you make anhydrides, okay? So the first reaction is an acid-base reaction. You make the carboxylate, all right? And then the carboxylate will react with the acid anhydride. CH3COCl is a shorthand notation for the acid chloride, okay? So we've talked about the mechanism for that, and you've learned that, okay? So that's reaction 1 here, all right? The second reaction, we're not going to show a mechanism for, but we've talked about it already. If you take a carboxylic acid and you heat it up to extremely high temperatures, you will get the anhydride, okay? And that's not very applicable to the lab where we don't have access to these very high reaction and high pressure reaction vessels, okay? Don't worry about the mechanism there, all right? The third reaction that I would like to talk about, okay, that we do need to learn, is if you take an acid anhydride, okay, and you treat this with water, you'll form the carboxylic acid, all right? Now, this is a symmetrical carboxylic acid. We normally never balance these chemical reactions, but of course you form 2 molecules of acetic acid from acetic anhydride, okay? So this molecule is called acetic anhydride, and this one here is called acetic acid. Don't forget nomenclature, and just try naming every molecule you see in these examples and problems in the textbook to gain more practice. So how does this reaction work? Now remember, water is neutral. It's really not an acid, it's not a base, so we're going to use neutral water here as the nucleophile. So here's water, okay? And the common reoccurring theme here is that we're going to attack the carbonyl on the left here, and we're going to kick off this guy here, which is the leaving group, okay? So chloride normally would be the leaving group, and here we're going to kick off acetate. So let's look at that. So here we want to attack right here like that, all right? And that's going to give us, once again, the tetrahedral intermediate. All right? And we want to kick off the leaving group. So again, remember, that's right here. This is the leaving group. That's acetate. All right? So take your lone pairs, move them down to make reform a carbonyl, and kick off that carbon-oxygen bond. So that makes acetate, and we're almost there to the carboxylic acid. The portion on the left looks like this, okay? And the leaving group looks like this. All right? And so what I like to do is just use the carboxylate to deprotonate that. All right? And so what you form is the carboxylic acid, technically 2 equivalents of that molecule, okay? So we have attack, and then eliminate, and then I don't know if you want to call this deprotonation or protonation, because the molecule on the right is doing the deprotonating and the molecule on the left is doing the protonating. So, you know, I don't know what you call that, okay? It's both. So it's AED or AEP, however you want to do it, okay? Now, so that's a reaction normally you don't want to occur. So if you have benzoic anhydride, okay, and it's an old bottle, eventually moisture from the air gets in every time you open it, and after a while it gets killed and you form benzoic acid, okay? And that's generally speaking an unwanted reaction, okay? So that was reaction 3. Reaction 4, okay, is ester formation, okay? So how do we make esters from anhydrides? So we have an anhydride, okay? And we can add an alcohol to this, such as methanol, okay? And this, again, is the leaving group. So we're going to attach an OCH3 there, okay? So the product we get is OCH3. Now, acetate's the leaving group, and that hooks up with the hydrogen from the methanol, so you form acetic acid, okay? And I'll just draw that over here, okay? And that's, you know, what becomes of the leaving group. So the reaction mechanism is very similar to acid chlorides, but let me just go ahead and show it here for the students that want to see that, okay? So again, we have methanol here, which is a neutral nucleophile here. And so we're going to attack the carbonyl carbon. Electrons go up to this carbonyl oxygen, okay? So that's A for attack. And now here's where we want to kick off the leaving group. So use your lone pairs. You can draw them in if you like, or you can draw the arrow coming from the minus charge here. So the electrons come down and reform a carbonyl, and this is the bond that breaks. You kick off acetate, okay? So that's the elimination step of acetate. Let's draw what we have. And I'll draw acetate below here. And what we want to do now is take that charge, or the negative charge, and use that as a base to remove the proton from this molecule here. And so that will give us the ester. Now, we normally are only interested in this part of the reaction. We're not interested in the leaving group. So many times we don't balance that chemical equation. Now, this is used a lot of the time for acetylations. Let me show you just in the very general sense. If you have an alcohol, oftentimes what you do is you treat this with acetic anhydride. Okay, there might be a base in there, maybe not. And that's going to give you an ester, but it's an acetate, okay? It's an ester derived from acetic acid, so it's an alkyl acetate, or it's an acetate, okay? So we call this an acetylation. So let me give you some examples. All right, so we might call this para-hydroxyaniline. And if you treat this with acetic anhydride, I should mention here that nitrogen is more electropositive. We've talked about atoms in the periodic table being more electronegative, more selfish with their electrons, and not as nucleophilic. Well, it turns out nitrogen is more generous with its electrons. It's more electropositive because it's more left on the periodic table, and so it's a better nucleophile. And so we're going to acetylate the nitrogen atom to make an amide. And this molecule here is trademarked Tylenol, or acetaminophen. Aceto comes from the acetate or the acetylation part, okay? Another molecule of interest is aspirin. So this is salicylic acid, and there's an alcohol, okay? It's a phenol, and if we treat this with acetic anhydride, we can make the acetate, or the acetylated product, which is known as aspirin. It's called acetyl salicylic acid. Chances are you're going to be doing this in the lab, and you need to know the curved arrow reaction mechanism for that, okay? So this is aspirin, all right? So let's go ahead and talk about, so there's the mechanism, right? So your fancy alcohol, whether it's from Tylenol or something, is going to attack the acetic anhydride, go through these intermediates, and give you, at the final end, an ester. Okay, so that's how the reaction works. Keep in mind that you might have a very, very complicated anhydride, such as this one here, okay? And you might add an alcohol to that to give you the ester. Or you might have a really complicated alcohol, and you might have a more simpler anhydride above the reaction arrow. But either way, you want to draw the ester, okay? So don't get confused what's shown above the arrow. Sometimes it's an anhydride, sometimes it's an alcohol. Either way, the two react and give you esters, okay? Sorry about that. The motion control keeps turning the lights off in this room, and I can't read my notes. The next reaction we have is reaction number 5. Okay, reaction number 5 is the creation of amides. So you can take an amine, such as ammonia. Okay, and ammonia will react with anhydrides. And again, we're adding excess. If you haven't seen my other videos, the letters X and S stand for the word excess. And the idea here is that you have more than 2 equivalents that are necessary to do this chemical reaction. From this chemical reaction, you form amides. Okay? You can form primary amides, or you can form secondary amides, or you can form tertiary amides, and these are reactions 5, 6, and 7. And the reaction mechanism works exactly the same as we saw with acid chlorides, except it's slightly different because, well, I'll show you, okay? So if we have a secondary amine, okay, we can make a tertiary amide, okay? So remember, nitrogen always has 3 bonds to it, so we remove a hydrogen during the chemical reaction from the reaction, which is an acid-base kind of step, okay? So let's look at some chemical reactions here. If we have a molecule that looks like this, now this is called propionic anhydride because we have 3 carbons there. And if we treat this with ammonia, and again we're using excess ammonia, we form this guy here, and we don't care about the leaving group and what happens to the second equivalent of ammonia, okay? So we're interested in the amide only. So how does this reaction work? The ammonia here is a sufficiently strong nucleophile, okay? And so again, the theme of this is that this is going to be the leaving group, okay? And so we want to attack right here, swoop the electrons up to the carbonyl oxygen, and that makes this tetrahedral intermediate. All right, so then what we want to do is eliminate the leaving group at this point. So we reform the carbonyl and we break the carbon-oxygen bond. And so the negative charge goes onto the carboxylate, okay? So that's the elimination step there. Now, at this point, we kind of go into a little bit about the amines. We have ammonia that's floating around, which is excess, right? And ammonia, you need to kind of memorize that amines are basic, okay? And I'll just put an asterisk on the top of this page. So when you want to do a deprotonation, use your amine. Okay, I don't want to go into pKa's and stuff, but don't use acetate, which is, you know, it'll make a strong acid, right? Use your amine to deprotonate here, okay? And what you form is so we're deprotonating that protonated amide to give us the amide itself that's neutral, so it has one less hydrogen, okay? So if you're starting with NH3, you end up with NH2 attached to your acyl or propionyl group or something like that, okay? The same thing would happen with a secondary amine or a tertiary amine, okay? I'm sorry, a primary amine or a secondary amine. So I'm not going to go through reactions 6 and 7 here in the video, okay? It's getting long enough. Now, reaction 8 is the reduction so the book says excess, but I never write excess because we all know that lithium aluminum hydride has extra hydride in it, okay? And so what you form here are 2 equivalents of an alcohol. Okay. Recall that if we have an acid chloride, and we do the same thing, so these are ditto marks, right? Just copy above. What you get is the same thing. You get a primary alcohol. So how does this reaction mechanism work? It works just like before. Okay. Recall that if you have hydride, that's hydrogen with lone pairs, right? So a negative charge is going to attack the carbonyl carbon, okay? And that's going to give you your tetrahedral intermediate, okay? Oops, forgot to draw all this stuff in here. And what happens is you kick off the leaving group. I'll draw that in maybe yellow here. Okay. You get an aldehyde and you get acetate. Okay. The aldehyde can react. This gives you a alkoxide that sits around until you add water. And that becomes protonated when you add large excess water to this to give you your, alcohol. I don't worry about the mechanism for my class for this particular problem, but that's basically how it works. Okay. Now, for reaction 9, we have the situation where we can do not lithium aluminum hydride, which is excess, but add lithium tritert-butoxy aluminum hydride. Okay. And this gives us an aldehyde. Okay, so it stops at the aldehyde stage. So recall that if you have an acid chloride, okay, and you react it with these same reaction conditions, it stops at the aldehyde stage because, remember again, that this reagent has just one hydrogen or one hydride there. Okay, so how does the reaction mechanism work? It does just as I showed before, but it just does it once. Okay, so I'm being lazy here with the mechanism. I'm just drawing H- rather than this very complicated aluminum complex. So hydride attacks, A for attack. You get the tetrahedral intermediate again. I believe you are beginning to see the pattern here, that we always collapse that by kicking off the leaving group. So that's E for elimination. Okay. And that's it. You've used your hydride. And we have just acetate floating around there. Okay. So it stops at this stage. All right. Next up, we have the reaction of anhydrides with Grignards. So that's going to be reaction 10. So Grignards and anhydrides. This is not really synthetically useful, but let me show you the reaction. So if we have an anhydride and we treat this with, once again, excess Grignard, what we'll get is a complicated mixture of things. So what we're going to get is a tertiary alcohol and, acetate leaves. I would not write that on the note card. I would just write this portion right here. Okay? So recall that if you have an acid chloride and we treat this with the same reagents, you get a tertiary alcohol with 2 new carbon-carbon bonds. So let me show you the mechanism maybe on the next page. Okay. So if we have an anhydride, and let's say I treat this with ethyl magnesium chloride, water, I will form this molecule. All right, so let me try to show you the mechanism for that. Whenever you have a Grignard, remember that that's a carbanion. Carbanions are a carbon with a formal -1 charge and a lone pair on the carbon. So that's a very strong nucleophile. That's going to attack the carbonyl carbon. Okay, and remember the goal is to kick off this leaving group here. So that's the attack stage. We get the tetrahedral intermediate. So I'm drawing my ethyl group down there. It's now attached to my molecule. And what I now want to do is kick off the leaving group. Okay, so acetates being removed. OAC is oftentimes how we can abbreviate acetate. And so we get, if we draw the molecule carefully, we can see how we have ethyl, well, we have 2-butanone there, okay? Now ketones, if you remember from chapter 20, I believe, can react with Grignard. So what happens is that we have another equivalent of our ethyl Grignard, okay? And that can attack the carbonyl carbon, push electrons up to the oxygen, giving us now an intermediate with 2 ethyl groups attached, okay? And the molecule kind of just sits there for a while until we decide to add water to the reaction mixture. And so the alkoxide becomes protonated in that step, okay? And that gives us the final molecule. Okay, the best way to learn these mechanisms is grab a blank sheet of paper, copy this right on top of the top, and then every day, just copy exactly everything, all the arrows, all the charges, everything. Do that once a day for 5 days, and then once a week until you got it. All right, there's a little bit of memorization, and just practicing going through the motions can help you, okay? So that's a tertiary alcohol, okay? So that's reaction 10. Reaction 11 is the use of anhydrides that react with your Gilman reagents, okay, to give you ketones. So recall that if we have an acid chloride and we react this with a Gilman reagent, it's just slightly nucleophilic. It's reactive enough to react with an extremely reactive acid chloride, but it's not a strong enough nucleophile source to react with ketones, okay? So it stops at the ketone stage, all right? So this is a reaction you definitely want to put on a note card. Review them often, okay? So how does this mechanism work? It works just like before, but I'll show you how it works. We have an anhydride, okay? Now I don't like R here too much, so I'm going to do a real live example. I'm going to do an ethyl Grignard, a diethyl cuprate, okay? So when you do a Gilman reagent, you treat it just like before in a lazy way as a nucleophile attacking the carbonyl carbon. So here's your ethyl anion. It doesn't come from the Grignard, it comes from this Gilman reagent, okay? This is a Gilman reagent. So take those lone pairs, attack, and I'll put this in quotes, just so you can know it's really not there, but it looks like it. And so what you get after this attack step is your tetrahedral intermediate. Your leaving group is poised. Okay, so here's my ethyl group. Now what we do is we eliminate and we get our 2-butanone. And this is where acetate gets expelled. All right? So that's it. Those are the 11 reactions. The textbook has like one paragraph. It says, all right, these all react just like the acid chlorides. Let's move on. Okay, but anhydrides are the second most reactive of the carboxylic acid derivatives. Remember, the acid chlorides are most reactive, and then we have anhydrides that are second most reactive. And they're very commonly used to acetylate molecules. We saw how Tylenol is synthesized and aspirin is synthesized, okay? So they are an important part of your sophomore organic chemistry, and probably you're going to do a lab involving aspirin synthesis. So thanks for watching. I hope these videos are helpful to you, and take it easy.